Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by David Schlegel, who's come down to us from UC Berkeley. David did his undergraduate work at Princeton, and then did his graduate work at UC Berkeley, where he was working on cosmic flows and galactic dust. Then he went across to Durham, England for his postdoc for 3 winters. And then he came back to Princeton, where he was working on the Sloan survey. And then 10 years ago, he returned to the West Coast, where he set up at Berkeley. He's currently the project scientist for the project that he'll be talking to us about today. He was the PI on the Big Boss survey as well. And he's going to talk to us how to use these spectroscopy surveys to look for exotic things like dark energy. So please join me in welcoming David.
Okay, great. Thanks very much. Everyone hear me okay? Okay. Okay, so I'm going to be talking about dark energy today from galaxy maps. And it's a wonderful job to be kind of a world-renowned expert in dark energy because we basically know nothing about it. So you have to know very, very little to be one of those world experts. So I'm going to tell you about what we're attempting to learn from galaxy maps for dark energy. And let me start with just a simple view of the cosmos as we understand it today, just on the largest scales. So the universe, it turns out, is dominated not by baryons, not by the particles that we interact with every day, but by both dark matter and dark energy. And so first there's dark matter, which was inferred, about 40 years ago now. And it was originally inferred from looking at the rotation curves of galaxies, where if you took pictures of galaxies and then took spectroscopy of the motions of these galaxies, what you found was that there wasn't enough matter in these galaxies to hold them together. So if you didn't have dark matter in these galaxies, the entire thing would just fly apart. So that was the original inference for dark matter. We have many other lines of evidence today. But what this means is if you put up your periodic table of elements and then the constituent particles of those, here's our standard model for the particles in the universe, so including neutrinos and muons and so forth. And what you see is this is missing 5/6 of the particles of the universe, right? So most of the mass, it's not in any of these. It's in, well, somewhere else, some slide we don't have yet. That's the other 5/6 of it, and those are the dark matter particles. Okay, then 15 years ago, what we found was there's something else in the universe which we call dark energy, which the term means very little. It's kind of the term for our ignorance, which is a descriptor of an observational fact that the universe is accelerating today. So the discovery 15 years ago was that the universe formed at a Big Bang. We already knew that. So that was 13.7 billion years ago. The universe is expanding, and then the expectation was, well, you have the force of gravity attracting everything to everything else, whether those be baryonic particles or dark matter particles, and that should be slowing down this expansion. So we all knew that. There was no reason to look, but a few people did look, and what they found was, well, in fact, that's completely wrong. What's happening today is the universe is accelerating. So this expansion has been speeding up for about the last 6 or 7 billion years. And this was discovered initially by looking at supernovae and looking at, this is a plot of the distance of supernovas as a function of redshift. And what we thought we knew 15 years ago was that the universe started in the Big Bang. It was expanding but slowing down, and then at some point it might collapse back down on itself. But regardless, it would just keep expanding more and more slowly. And in fact, the data didn't show that, but what it shows is that the universe is on this curve right here where now we're accelerating. So this was the original discovery of dark energy. And when we draw up our picture of what the universe is composed of today, what we find is, so it's only, about 4%, 5% baryons, 5 or 6 times more dark matter particles, and then the universe is actually dominated by whatever is causing this acceleration today. And that's what we're calling dark energy. Okay, so there we are. What I'm going to tell you about today are maps that we're making of the universe to try to understand this better. And so let me start with the question of what is a map? And a map, at least the way that I think of it, is you take any particles or distribution of stuff in the sky, and you can put these particles on some three-dimensional map. And in addition to that, you can measure dynamics of these maps. So you can measure not just the three-dimensional x, y, and z positions of objects, but also their velocities. So usually I think of these maps as 6-dimensional maps where you have your 3 spatial dimensions and then your 3 velocities. Okay, and so it turns out, historically, we've learned a lot from making maps like this. And if you go back to early maps of the solar system, so you can make these maps of where all the objects are in the solar system. So the planets, 8 or 9, depending on how old we are. My kids actually still say 9. And then you can put these on 6-dimensional maps of their positions and their velocities. And what you know is that these maps have to be consistent with, both whatever the initial conditions were for forming the solar system, but then also the physical laws governing the solar system. And from these maps, for example, it was in 1769 that some aspects of these maps were used to infer the scale of the solar system, which before 1769, there was actually uncertainty of about a factor of 2 in how big the solar system was. And then after 1769, this was measured to about 2% precision using transits of Venus in front of the sun. So I hope everyone saw there was a transit of Venus, what was it, 2 years ago now? So I hope you saw that because I think it's hundreds of years until that happens again. I'll be there to see it, but I don't know if everyone plans on living forever. Okay, then I'm not going to go into it, but there have been other aspects of these maps of the solar system used to show that Einstein's theory of general relativity was correct and so forth. Okay, so let me move on to maps of the universe. So just as historically we've made maps of the solar system, we can also make much larger scale maps of the universe. And again, it's the same thing that we're trying to do, where we say these maps of the universe, they have to be consistent with whatever formed the universe originally, so whatever those initial conditions were for the universe. And then also the laws of nature, the laws of physics that are governing the dynamics of the universe throughout its history. So just insisting upon that consistency turns out to be very powerful. Okay, so what we have is we can make maps, and in fact we can make maps throughout the history of the universe, because the more distant objects that we're looking at when the universe was much younger. So this is a snapshot of different time slices through the universe, where this is a picture of the microwave background from, I can't remember if this is Planck or WMAP. And then we can make maps of the universe at different times up until today. And all of these maps have to be consistent. Okay. And then one technical point I'm going to make here is if you make maps on large enough scales, then you're still in what we call the linear regime, meaning that there's still a mapping between these maps that we're making today and the initial conditions of the universe. So if you go on small enough scales, like the scale of a person or the Earth or the solar system or the Milky Way, then you're in this nonlinear regime where everything's been mixed up in phase space. But if you go on large enough scales, objects haven't moved far enough such that wherever there's an overdensity of material today, there was an overdensity in that phase space of the universe when it was formed. And in fact, if you ask how many of these volumes of the universe there are between, this is a calculation done between us and redshift of 1, so about halfway across the visible universe. It turns out that there are about 100 million, what we call 100 million modes that you could measure in that volume of the universe. So that's kind of just a useful number to be familiar with, because those are the number of unique linear measurements. Okay, now mapping the sky. So it turns out there are some challenges to mapping large volumes of the sky. And the challenge is most telescopes are really not designed to do this. So if you look at, for example, the Hubble Space Telescope and say, well, let's build some three-dimensional or even a two-dimensional map of the universe using the Hubble Space Telescope, you'd think it's expensive, it must be good, maybe it's the best telescope to do this with. Well, it's really not, because it hasn't been designed to do that. It's been designed to look at small patches of the sky, as most telescopes are. And so I put up a picture of this girl. I should replace this with a picture of one of my own kids. But using the Hubble Space Telescope, it's like taking a soda straw that's 8 feet long and then looking at some patch of the sky through that soda straw. And so you can work out, well, how long would it take to even image the full sky with this telescope? It works out to about 200,000 years. And so I haven't been able to attract graduate students to do that. Fortunately, there are some telescopes designed to look at larger patches of the sky. And so this is a picture of the telescope we've been using for the last 15 years to do this. So this is the Sloan Telescope at Apache Point, New Mexico. And so this is a telescope where instead of that tiny field of view, its field of view is 3 degrees diameter. And just for reference, the moon or the sun, that's about half a degree. So it's about 40 times the size of the full moon. So that's the patch of the sky I can see at once. And it's even a little bit bigger than HST. And then I have to show at least one picture of Jim Gunn. So this is the original project scientist for the Sloan Digital Sky Survey. And so you can take what you will of this picture. I think he's aged well. Okay. So the first thing that we did with the Sloan Telescope was construct just a two-dimensional flat image of the sky. And so we did this with what at the time was the most expensive CCD camera in the world. So this is a CCD camera that's about this big. Actually, it's exactly this big, as it turns out. So 30 CCDs, it cost about $6 million. If you'd like to see it, it's now in the Smithsonian. But we use this to image the sky in 5 filters. And so this is our image of the sky that we've constructed, which we've used for a lot of science projects. It's also available from Google Sky. So if you go to Google Earth, somewhere there's a click button where you can say, look up instead of down. And then it's all of the SDSS data. So we finished that image of the sky. I mean, I hope we did, because we gave the camera away. And then we've released, it's the largest color image of the sky. It's about 1 terapix of data. And in this image, it's about 250 million galaxies and 250 million stars. So at the moment, that's still the largest just image of the sky. So that's relatively easy, making a two-dimensional map, but that's not really what I'm interested in. What we really want are at least three-dimensional maps of the sky. So the 2D maps, that's easy. You just need to take a picture. A 3D map, that's certainly more work. So to make a 3D map, you need to disperse the light, get spectra of objects in the sky, and then from those spectra measure redshifts and distances of galaxies. So this turns out to be a lot more work. But we've done this with the same telescope. So this is what something like 80% of the time has been used for on the SDSS telescope, is not those two-dimensional images, but getting spectra of objects and turning this into three-dimensional maps. So here what I'm going to do is I'm going to walk you through all the steps that we go through to start with our two-dimensional maps and then end up with the three-dimensional map. Okay, so we start with an image. And from this image, we identify galaxies that we'd like to put on this three-dimensional map. And when we started the SDSS, we actually did this by picking out the million brightest galaxies on the sky, where a galaxy in this context meant anything that was fuzzy. So anything that looks like a point, well, that's probably a star. Anything that's fuzzy, well, it's probably a galaxy. And so we did that. I'm not actually going to show that at all, because what turns out, which you would have known in advance, is the million brightest things on the sky, well, they're all relatively nearby. So we got this wonderful map of 900,000 galaxies. It's been incredibly useful, but it turns out it maps this tiny fraction of the universe, because it only goes out to redshifts of 0.1 or 0.2, just because we intentionally looked at the million brightest objects. So instead, what we're doing now for the last 5 years, we've been picking out objects that we know we can use to trace out a much larger volume of the universe. So we start with this map of the sky, and it turns out you can do very well by just saying, well, let me take these fuzzy objects, because I know they're galaxies, but let me also pick out ones that look like they're red. And that very simple cut works very, very well, because it turns out the reddest objects, they're both the most massive galaxies in the universe. Just by chance, the more massive galaxies, they formed earlier. They have a lot of older stars. Those older stars are redder. And they're also at greater distances, and they're redshifted, so that makes them yet again more red. So in fact, by just making some very simple selections of saying, let me get the reddest fuzzy things on these pictures, you've selected out the objects that you think are going to be the highest redshift galaxies that we can see. So that's what we've done. We take patches of the sky that are 3 degrees in diameter. We select out on each one of these 1,000 fuzzy red things, mostly. We're also selecting quasars, as it turns out. Oops. And then we turn this image of the sky into an aluminum plate. So it's not actually made out of gold. Maybe if this were a NASA project, it would be gold. I don't know. But, so ours, unfortunately, is only aluminum. So the metal here is worth about $10 instead of, what it would be, $20,000. So what we've done, though, is everywhere where there's a galaxy of interest, we've drilled a precision hole of the location of that galaxy, such that if this aluminum plate were looking up at the sky, then these holes would line up with those 1,000 objects. So this is turning our map of the sky into an aluminum plate. And what we're doing here is we're taking all of the objects on this plate. We want to get spectra of these objects. And so we're selecting out these objects then with optical fibers, which if you'd like to try plugging plates later, you're free to. So this is a set of 20 optical fibers, where these are the same as telecommunication fibers, in fact, bought from the same companies. So there's a little fiber in the middle, diameter of 120 microns. And then we actually have someone who plugs these fibers into each one of these holes. And so every day we're plugging thousands of fibers into these drilled holes. So we have one person who's done this about 1 million times. And so you can see how fast you can do it. But these guys, they've been doing it for years. They've gotten very good at it. So once we do this, then all of those fibers, they feed into a cartridge that feed into a spectrograph that's mounted on the back of the telescope. And I'm not going to explain the details of it, but if you're interested, this is the instrument on the back of the telescope, which is a pair of spectrographs with gratings and so forth that disperses the light. Then it feeds detectors that are actually made at Berkeley Lab. So these are the most sensitive CCD detectors in the world. So if you're interested in these, I can tell you more about these as well. And then we get data. So I have to show you what raw data looks like. This is what our data looks like coming off the telescope. So this is actually the world that I live in. So occasionally I get to give fun talks like this, but much of the time I'm looking at data like this that comes off the telescope. And what you're looking at here is this is just a little section of one of our exposures on the sky where we have fiber number running in this direction, where each one of those fibers produces a spot on this image, and then it's dispersed in this direction, where now this is the spectrum, this is the wavelength. So this is fiber number wavelength. So each object has these sets of spots, and you can see most of them look identical. And what that is this is a spectrum of the night sky. And it turns out a spectrum, an optical spectrum of the night sky, it's dominated by all of these OH emission lines. So pretty much every hour we get 1,000 spectra of what the night sky looks like, which in of itself is not interesting at all. But buried in here, and I can't even see it here, buried in here are spectra of these distant galaxies, but it's very much fainter than what you see in this image. So we take sets of these images. This is what most of those spectra look like. And so all of this are night sky emission lines. And all I want you to see here is it's a very busy spectrum. There's lots going on. The scale of this in whatever these units are is 100. And then our galaxies are much fainter than this night sky. So this is a spectrum of one of our galaxies. Can't really see it here, but the units here are 1, 2, 3. So it's much fainter than the night sky. But that's okay. We can model what the night sky looks like. And once we do that, then we can fit models and redshifts to each one of these objects. And so this gives us a redshift of this particular galaxy. So this is that redshift of whatever it is, 0.3 or something. So there are well-defined features in all of these spectra. And once we do that, then we can put these on a map. It's actually a three-dimensional map, where this is a slice through the sky that we've made with SDSS, where all of these are galaxies between us and about redshift of 0.7 here. Turns out we have almost no data between redshift of 0.7 and 2.1. And then we have a smattering of data between redshift of 2.1 and 3.5. And these are from distant quasars. So that's our map. It's a rather incomplete map, but it's still the best one that we have. And then this is my favorite, if we just turn off the lights for a minute. Okay, so this is it. So this is the real three-dimensional map of the sky. And so if you ever watch the opening of Star Trek or Star Wars or whatever, they show some movie that looks something like that. But the difference is this is real. So this is the real universe that you live in. So what this is this has postage stamps of our actual color images of more than 1 million galaxies placed where it really is in three-dimensional space. Okay, so when the aliens abduct you at some point in the future, you have to make it back to the Milky Way galaxy. This is your map. Okay, I can cut the lights back on.
Is there a way to see that, say, on YouTube?
Yes, so I think this is on YouTube. It might be a lower res version, so if you'd like a nice high res version, I can give that to you. Okay, so from these data, we can actually infer the scale of the universe as a function of, I'd say time, but redshift really. And what we've done is we've made measurements of the scale of the universe. We've made, this is that same plot of what the expansion history of the universe has done as a function of time. So we have the Big Bang at 13.7 billion years ago. We have a measure of the scale of the universe when it was only about 2 billion years old, and these are from quasars. We have no data up until redshift of 0.6, and then we have several data points between there and today from our galaxy maps. So that's what we have. And these measurements, they're actually 1% to 2% precision measures of the scale of the universe. So today, we're making measures of the scale of the universe that are comparable in quality to what we knew about the scale of the solar system back in 1769. Okay. To date, these data, they fit a model of the universe where we only need 5 fundamental numbers to describe those data. And so I've listed what these are. These numbers, these imply something about dark energy. But what it tells us is right now, this is all consistent with our simplest picture of what dark energy could be. So injecting what we call a cosmological constant into Einstein's equations does fit the data. And we've tested deviations from the simplest model, and so far we don't need them. So what we find is this 5-parameter model, it does fit the universe to the precision of the data today, and it looks like the universe is also mathematically flat, which we could talk about later, but flat actually having a mathematical meaning here. And so I've included here, these are from some of our press release coverages over the last couple of years. So this was one of our first results from the Sloan BOSS survey where, anyway, the newspapers are much better at presenting these results than we are. So this was saying, well, it looks like so far Einstein was exactly right. You could fit what the universe looks like with the cosmological model. So this was a fun article because, so this was in the Daily Mail in the UK. Einstein's exactly right. And then you keep reading this article down on page 5, and then the rest of the article is, and by the way, Einstein's brain is now on display at the Wellcome Trust in London. So clearly some editor got these 2 pieces of news in on the same time. Okay. The other thing that we can do with these maps, though, is we can use this to measure the scale of the universe at different epochs. But since these data, it's on such large scales that material hasn't moved around very far, it is a picture of what the universe looked like shortly after the Big Bang. So in fact, this was our broad timeline of what the universe looks like, where you have the Big Bang, the universe is expanding, slowing down. Somewhere around 6 billion years ago, it starts speeding up again. So this is the big picture view over 13 billion years. But you can actually focus in on just the first fraction of a second of the universe, where we think something else was going on called inflation, in just about the first 10 to the minus 35 seconds of the universe, so in here. And what we have is, it's a map of what the conditions were in the universe after it exited this inflationary period of a fraction of a second. So these maps that we're making today, it is a map of what the universe looked like after exiting the inflationary period of the early universe. So this is actually a way to probe this first fraction of a second of the universe. This is well before the elements formed or anything else. And our hope is that by studying just this first fraction of a second of the universe, this will tell us something about different theories about how the universe formed. So if you see in the popular press, there are all the articles about multiverses, multiple universes, all the different ideas of how the universe could have formed, extra dimensions. But it turns out these theories would imprint something on the universe that now we can actually hope to measure through these maps. And in fact, I have to show this figure, which just people hate it when I show this figure, but I think this is the most interesting figure to come out of cosmology in the last many years. So I'm insisting on showing it. Okay. So what this is this is actually from the Planck overview paper from a year ago, combining the microwave background results from the Planck satellite with the results that we have from the Sloan Digital Sky Survey, these three-dimensional maps. And looking at the conditions affecting this inflationary period of time in the universe. And so these are constraints in a parameter space of these parameters, and we're actually making measurements of, in cosmology, it's some number that's not 1 or 0, in whatever units that you want, but it's actually a measure of something about the features in this post-inflationary epoch. So you should stay tuned to future results from these sorts of analyses, because this is actually probing something about this period. Okay, how are we doing? I'm actually ahead of schedule, okay. Okay, so we've been making these maps for 15 years now. I said the original SDSS, we were just looking at the million brightest galaxies of the sky, so it was a tiny fraction of the volume of the universe. But even with what we're doing today, with what's called the BOSS survey in SDSS, we've actually only mapped at something like 0.5% of the volume of the universe, very sparsely. So after all of these years, that's the map that we have. And what we'd like to do is actually fill this in and get a more complete map between the high redshift universe and today. And in particular, explore this period of time when we went from a decelerating universe to an accelerating universe. So at some point, 6 or 7 or 8 billion years ago, dark energy started to become the dominant energy in the universe, and that's actually hardly explored. Okay, so the question is how to get there. And we're pretty much reaching the limit of what we can expect to do with the circa 1900 technology of switchboard operator plugging fibers into plates. So to date, we've plugged something like 3 million fibers into holes. If you'd like to extend that from 3 million to 30 million, it doesn't actually scale very well. So we're actually looking at technologies moving beyond this plug plate. I guess I can call it a technology. I'm being generous there. And we're also moving to a larger telescope. So the Sloan Telescope, it's a 2.5-meter diameter mirror. And the next big project we'll be doing, it's at the 4-meter telescope at Kitt Peak in Arizona. So this is a picture of that telescope. So the telescope built in 1971. The hope here is that by making these more complete maps of the universe, we can actually really test between even just these most basic ideas of what the dark energy is. So whether you're modifying GR, whether there's a new field in the universe, or whether it's a dynamic field of the universe, something that changes as a function of time. So these are the questions that we can ask with a more complete map. And so this is the telescope we'll be using. So this is the Kitt Peak 4-meter telescope, or the Mayall telescope. It's built in 1971. And then in 2009, we had an optical designer who discovered a wide field solution on this telescope. So this telescope right now, it doesn't see a particularly large field of the sky. So it turns out optics are still an art. It's still undergoing advances. And so it was March 6, 2009. I remember it well. So he discovered a wide field solution on this telescope that would give us the same sort of field of view that we have with the Sloan Telescope. So this 3-degree diameter field of view. And then this telescope, the other nice thing about this telescope is that it has a moving weight of 375 tons. And you might ask, well, why is that a good idea? Well, it turns out it's a good idea because you can park many tons of instrument anywhere on this telescope, and it just doesn't care, right? I just added 6 tons. Oh, just add a counterweight. That'll be fine. There must be some limit, but we're not exceeding that limit. So what we'll be doing is up at the what we call the prime focus of this telescope, up here, we'll be replacing the current instrumentation at that point on the telescope with a focal plane that's no longer this plug plate system, but is something that's robotic. So this has been a lot of fun for the engineers, where we have this engineering challenge of we don't want to be doing this anymore. But what we want to be doing is having robots that are moving fibers around quickly. And so the scale here is about 1 centimeter, where this is just a blow up of a 1 centimeter section on this focal plane. And so what we're building is something that has actually 5,000 robot fiber positioners, each one with 2 motors. So 10,000 motors sitting up on this focal plane, reconfiguring 5,000 fibers in under 1 minute. So this is the design goal for this instrument, where every 20 minutes we'll be able to push a button, reconfigure this focal plane of 5,000 fibers, and then take our next exposure. So where we'll be going is this is a slice through, again, the universe that the map that we've made. So nearby galaxies, distant quasars, in between there, terra incognita, yes. Again, very little data here. And we'll be filling this map in with about 30 million galaxies. So this will be a much bigger map of the universe. And then somewhere in here is where dark energy is starting to become dominant. So we'll actually be able to map this out and map out the transition from dark matter dominated to a dark energy dominated universe. And going back to this question of scales again, so what we're doing, it's these geometrical measures of the scale of the universe. And that's a hard thing to do, right, is to measure the scale of anything cosmological. our first somewhat accurate measure of the scale of the universe was made with the Hubble Space Telescope 20 years ago. So this was actually the key project for the Hubble Space Telescope, was to measure, I don't know if you remember this, there was the Hubble parameter controversy where there were factors of 2 in the opinion of the scale of the universe. And I call it an opinion because there was one camp who said the Hubble constant is 50 kilometers per second per megaparsec, and then there was another camp saying, no, it's 100 kilometers per second per megaparsec. The supposed error bars were 10%, so they couldn't both be right. Turns out the answer is 70, so they were both wrong. But this was a major breakthrough for cosmology, was actually measuring the scale to 10% precision. So it was done about 20 years ago. And what we have today are measures of the scale of the universe to 1% precision. And so these are maps from the Sloan Telescope, where we have maps from the microwave background at 400,000 years into the universe, and then these maps at later times. And a lot of our results have just come out in the past year. So in fact, our most recent results came out April 6th of this month. And these were our maps at redshift of 2.3 from quasars. And let me finish here. So it turns out I'm finishing early, which is great, so we can have questions. So eventually, we hope to be discriminating between, I'm just listing a handful of the theories for what's causing dark energy. So eventually, we'll have a handle on discriminating between these different theories, as well as getting a map of what these initial conditions were from the inflationary epoch of the early universe. So let me end it there, and then we have plenty of time for a discussion.
Okay, I'll come around with the mic. David, could I ask you to go back to the slide where you were showing the annoying plot, or the thing that you were, could you go over that in a little bit more detail about why people are annoyed and
Which annoying?
the Planck, it was the Planck survey overview paper plot.
All right, okay. I'll find where I put that.
That one, yeah.
Yes, okay.
Can you discuss in a little more detail what it's actually showing?
Yeah, so what this is, this axis right here, so this is called primordial tilt. So this is the scale of fluctuations in the universe where, to first order, everything looks scale-free, meaning it's like a fractal of whatever the dimensionality is for, well, I guess all fractals are the same on all dimensions. So yeah, I hate to use the term fractals, but if this were unity, what that would mean is that you have the same sorts of fluctuations on any scales that you picked out. So there'd be no preferred scale, and that would tell you that this inflationary epoch somehow made the universe homogeneous on all scales, at least all scales within the observable universe. And that is in fact not what you see when you combine these two data sets together. Well, actually, you can see it from the Planck data alone, but much more clearly combining the Planck data with the Boss data, where you're looking at, I mean, it really is looking at maps on all different scales and asking if these fluctuations are scale-free or not. And it looks like it's not to, I forget what the number is, at least 3-point-something sigma, where it departs from the scale-free number. So that there's some sort of scale, and this tells you probably something about the end of the inflationary epoch in the universe. But if you want to know more than that, you should actually ask a theorist and not me.
Hi, over here. When you showed us the map that you would like to make of the observable universe, it's not really a 3D map, it's a 4D map because it goes back in time. So in one map, you're like creating a 3D model where this is where stuff used to be and this is where stuff is now, all in one 3D thing. So how do you read a map that time is not constant from one side of the map to the other and extract useful models about where things that were somewhere are now and where things that are somewhere were then? And
Yes, that's a very good question. Let me just pick out. Sorry, bear with me for a moment.
Away because it's really sensitive. Just hold it out there.
So I'm actually going to say it's even, oh, it's not showing, okay. Well, it's even worse than what your question is implying because we're not actually even measuring just the 3D spatial positions of objects because we're measuring redshifts of each of these galaxies. And the redshift it's actually a combination of one of these coordinates, call it the radial distance. So it's a combination of radial distance plus one of the velocity components because it's line of sight velocity that defines its redshift. So we don't even have, even if you take a narrow slice through these maps, it's not even really a map of that slice, but it's a map of that slice redshifted. So that radial velocity added on to what you'd like to be your third distance coordinate. So to answer your question, though, the way that we're analyzing the data to date, well, the way that you could think about it, or the way that I like to think about it, is what we have is we have these maps where we have two angular coordinates on the sky. Then we have a third coordinate that's redshift. And there has to be some mapping between what that redshift is and what distance is. And if you do that mapping incorrectly, then you see all sorts of odd things in the universe. And so one of the things that you see is that it's not rotationally symmetric. So features that should be sphere-like would then look elongated or squashed. So what you need to do is put in this this remapping, let's say, from redshift to the third spatial dimension and do it correctly such that your map actually just looks right. So fundamentally, that's what we're doing. In practice, what we do, since we have kind of so little data today, all we do is we really do just take these maps and then slice them up in redshift bins. And we say, okay, for these galaxy maps between redshift of 0.45 and 0.65, let me construct what that map looks like using some model for what that remapping parameter is, and then make a measurement at that kind of median redshift.
it's like having multiple maps.
Yeah, so we're just, right now, we're just dividing it up into different distances, and that's how we're analyzing it. But in fact, you're right. The right way to think of it is we're kind of stretching this entire map in the third dimension to get it right.
My question has to do with the distribution in space of dark matter, dark energy. Okay, and I was thinking when I read the title of the talk that that's something that would be probed by this, but apparently we're a long way from there, aren't we? We're talking about dark energy as just this property of the universe as a whole.
That's right, and that's really just the data today is really only good enough to say, let me just imagine that it's some constant that may be a function of time, but is not a function of space, and then make a measurement. And that's really all you can do with the data today. Now, it could be if, I don't know, if dark energy is a field that is dynamically turning on in different parts of the universe at slightly different times or something, that would imprint then differently in different directions of the sky. It would still have to be consistent with what we see in the CMB maps, and that's actually a pretty powerful constraint. But aside from that, so you'd have to be consistent with that, but aside from that, yes, you could say it's manifesting differently in different parts of the sky, but we have not tested that.
I have two minor misunderstandings, one of which was related to the dark energy expansion plot. The original supernova data provided a calibration between redshift and actual distance. Now, is your remapping parameter doing the same thing and allowing you to put points on that curve back in time? Because you have redshift, are you then somehow deducing distance?
So what we're doing, it's...
I have a second part to it.
Okay, so it's the question between what we're mapping versus what the supernovae are mapping. Let me see if I have that here. Okay. One part of the answer to your question is we're geometrically measuring somewhat different things. So what we're measuring are angular scales on the sky from, it's actually the same acoustic features that we see in the microwave background. And let me just see if I have this image here somewhere. Somehow I dropped this from my talk, but this is a map of the microwave background. So this is at 383,000 years, what the sky looked like, where what your eye picks out here is the sound wave scale on these maps, which is measured now from the Planck data to something like 0.1% precision. So that we can just write down from first principles of physics what the scale of these features should be in the CMB. And what this gives us then is it's a physical ruler at the surface of the last scattering in the universe at redshift of 1,000, so in the distant universe. And it's actually exactly these features that we're measuring in these galaxy maps. So what we're able to do is tie redshift of 1,000 to these galaxy maps that are more nearby. So we're kind of working from the microwave background up until the local universe, whereas what the supernovae are doing, it's kind of approaching it from the other direction, where they're calibrated to the distance scale in the universe nearby from Cepheid stars fundamentally, and then stepping out to more distant galaxies. So actually we're making then this history of the universe coming from two different directions, where the supernovae are working from the nearby universe more distant, and these galaxy maps are actually working from redshift of 1,000 to more nearby.
Okay, the second part of my question related to that map of tilt versus tensor scalar that you brought up before from his question. Is the vertical axis, which you didn't discuss at all, the tensor scalar, is that related to this recent discovery of the inflationary B modes? Does that actually give an amplitude along that axis?
Yes, that's right. So that gives us an amplitude on the axis.
It's supposed to be higher than people thought.
Yes, yeah. So that's another kind of clue to the puzzle here. So this is all going to fall out very interestingly in the next couple of years, I think.
Yeah, my question relates a bit to this image here. Do we find an actual correlation between features in the surface of last scattering and the map of the galaxy clusters that you see?
Yeah, so you would if you waited billions of years. So the so this is a slice of the universe at 380,000 years, and then wherever there are overdensities here, which are the cold spots in blue, eventually that'll turn into clusters and superclusters of galaxies. So if you take a picture of the sky a billion years from now, then you should see galaxies starting to form wherever the blue spots are in the CMB.
Okay, I'm sure there are actually far more questions out there, but I know they're probably going to be waiting their chance to come and assault you at the podium, David. So I have a special, well, it's a dark mug. You might be able to fill it with some dark energy of your, a liquid dark energy of your choice, working late on the upcoming surveys. So please join me in thanking David for his great talk.